fully understood by science fiction authors everywhere. Truly the bane of the aspiring astrophysicist, these creatures are anything but easy to wrap your noggin around. But wait, you say you too want to get in on this wormhole action. But of course, this entirely uncontrived production appears to have been conveniently set up in advance specifically for that particular purpose, and how. All that being said, let us foray into the depths of this transient beauty post-haste. Chapter 1. The Black Hole. Ah, yes, there it is. Lovely. What's that? You don't see what black holes have to do with wormholes? Well, it's actually very simple. You see, Alright, let's pretend you don't know anything about black holes. It's black. It's a hole. To put it simply, a black hole is a celestial body that creates a gravitational well so steep that not even light can escape it. That is to say that the escape velocity of the object is the speed of light. Now, let's say that the black hole has no charge and isn't rotating, because that makes my life a lot easier. Since the escape velocity is the speed of light, and light speed is the ultimate cosmic speed, space-time behaves rather strangely in the vicinity of this object. Allow me to stress that a light speed escape velocity means that literally nothing gets out. In terms of space-time curvature, that means that whatever paths light and therefore anything else can take are all warped to point further into the hole. In the perspective of the observer, the black hole expands to consume their field of vision until there is no way out. That's just the thing about event horizons. What happens behind an event horizon stays behind an event horizon, where space and time as we know them cease to make sense. Now, the way things usually go, objects that fall through the event horizon are all pulled into the singularity and crushed into infinite oblivion. But here's the kicker. This funnel doohickey need not converge into a singularity. In fact, if you just cut off the piece with the singularity and glue the new shape to another just like it, you get something interesting. Namely, a wormhole. In this sense, it can be shown that black holes are merely a form of degenerate wormhole. However, this only works if the wormhole is held open internally by a negative energy density. Positive energy densities result in the singularity being reached before the cutoff point is attainable. However, negative energies have only been demonstrated to exist in very small amounts, as was observed in an experiment in which the vacuum of space pushed together two metal plates. This is called the Casimir effect. Regardless, it is convenient to imagine large negative energy densities for the purposes of hypothetical wormholes. The common wormhole analogy in 2 dimensions is a piece of paper with a line drawn over its length and 2 holes at either end. By bending the paper such that the 2 holes overlap, one demonstrates how the path through the holes is significantly shorter than that through regular space, i.e., traveling along the paper. This generalizes well to arbitrary dimensions, as the circular hole becomes spherical when extrapolated to 3 space, hyperspherical when extrapolated to 4, etc. In 1 space, all 2 shapes condense into lines, and in 0 space, wormhole travel is infeasible. This concludes the black hole portion of the video. Please hold your questions until the conclusion of the presentation. Chapter 2. Wormhole Anatomy. What is a wormhole exactly? In this chapter, we'll be taking a more physical approach. A wormhole has 2 mouths, one at either end, and a throat in the middle. It slots neatly into the surrounding space, never creating discontinuous tears in its surroundings. Of course, the wormhole mouths can be individually manipulated, opening up a number of interesting configurations. For instance, a wormhole is nigh totally dissociated from the main body of the surrounding space. Therefore, the length of its throat is entirely arbitrary, save for a few factors science has yet to hammer out. This means that a wormhole can actually be longer on the inside than the outside, all the way to the extreme case in which the wormhole's 2 mouths fully coincide and passage takes you nowhere. Also, though entirely theoretical, there is nothing preventing wormholes from having 3 mouths, or 4, or any number whatsoever. This is also true of the number of throats, so long as the interior is continuous and smooth. However, it is not obvious there exists a metric for determining how each mouth should be accessed in these cases. Additionally, it should be noted that the mouths of the wormhole are time-independent. That is to say that isolating the mouths in different relativistic gradients will desynchronize them. Interestingly, since the interior of the wormhole must remain smooth in all reference frames, travelers who enter one end of a wormhole must exit at the same time, even if the mouths were desynchronized when they went in. This property and more is further explored in the following chapter. Please hold your questions until the conclusion of the presentation. Chapter 3. Consequences of Wormholes. Closed time-like curves. Let's begin with an introduction to what is known as Minkowski space. It's a mathematical approximation of true space which gives us plenty of room to work with. Here on this Minkowski diagram, we have a horizontal space axis and a vertical time axis. We choose the units of the time axis to be large, such that light travels at a 45-degree angle to the time axis. We'll define an object at the origin of the graph to be our handy observer. Since nothing can go faster than light, we can extend a triangle into the future and the past to represent possible trajectories for that observer. We can also draw additional objects with their own cones. If their cones intersect ours, it is possible there was an interaction anywhere in the area of that intersection. Of course, if we know what path the object or observer takes, we can just draw it in the conical area from the bottom to top. This is known as a world line, a specific type of time-like curve. Note that at no point do world lines have a slope exceeding 45 degrees from the time axis. This is the definition of time-like. Because of this, there are no frames of reference in which time runs backwards. Therefore, no world lines can complete a loop, at least not without the presence of a wormhole. A closed time-like curve permits an object or observer to interact with itself in ways that usually shouldn't be possible. For instance, a billiard ball, fired through a wormhole, may prevent itself from entering said wormhole, or it may cause itself to enter the wormhole in the first place. Obviously, it is clear that closed time-like curves are ontological nightmares as real as wormholes themselves. Multiply connected spacetime. Multiply connected is a fancy word that means somewhere on the surface of your space there's a loop that you can make that can't be contracted to a point. A torus has two such loops. Generally speaking, any Euclidean space, even when deformed, has no such loops. But once again, wormholes make everything more complicated. First of all, a wormhole totally removes the angle sum restriction from regular polygons. You can have a triangle with 3 right angles, or even a shape with one side. This observation lies in tandem with a radical alteration of something called the Euler characteristic. To find the Euler characteristic of a surface, first you must draw polygons all over it. Then, you take the number of vertices marked, add the number of enclosed regions, and subtract the lines drawn between the points. For a closed flat space in 2 dimensions, the Euler characteristic is 1. But with wormholes, the Euler characteristic can take on strange fractional values. In the case of the right monogon, it is clear there is 1 vertex and 1 edge. However, the number of enclosed regions is not clear, so our usual method fails us. Thankfully, the Gauss-Bonnet theorem for closed Riemannian manifolds with piecewise smooth boundaries is here to help. Since the curvatures of the space and its boundaries are both 0, the first 2 integrals disappear, leaving only the angle sum. From there, finding the Euler characteristic is trivial. Simply divide both sides by 2 pi. We find the Euler characteristic of the right monogon to be 1/4. To generalize to any polygon, notice that the Euler characteristic becomes the angle sum divided by 2 pi. This extends even to manifolds of higher dimensionality, though it is much harder to show this. It is also notable to mention that strange polygons are constructible in an elliptical space, although wormholes do not actually change the flatness of their surroundings in a mathematical context. Finally, it should be said that the nature of multiply connected spacetime violates all manner of natural laws, such as the conservation of energy and momentum. Space lumping diagrams. Space lumping diagrams are an original method of observing the ways that wormholes pinch and distort the space around them via a grid and some numbered axes. Though they have little functional purpose, it is still a neat visualization trick, though it is harder to visualize them the more wormholes are added to any one graph. It is important to note that a diagram of this type always demands 1 dimension higher than the starting set, to which the wormhole mouths are constrained. This is analogous to how the throat of a wormhole is not physically embedded in the space being distorted. There is no real right way to draw one of these, but the idea is to show the curvature of the resultant space around the wormhole. Now, you may be asking yourself, is anything this guy just said actually true? The answer is, let's find out. The following is a simulation designed to show off some of the properties described earlier in this video presentation. potential energy going into the kinetic energy of the fall is extracted from nowhere, a violation of conservation of energy. A sudden change in direction is a violation of conservation of momentum. All of what you have heard today is true, probably. Hopefully, that clears up any educational ailments you possessed at the introduction of this video presentation. If not, I will be taking questions following the ending of this video, which should be coming up right about